Okay, so let's go right into an example then. 2, -4, 2, -2 is our matrix. We want to find general solution to AX equals X prime. Okay, so we have this theorem that says we should try to diagonalize A. We should find the eigenvectors and eigenvalues. And if it is diagonalizable, then we get n linearly independent solutions. So in this case, 2 linearly independent solutions, which are, so let me just write this down. There's this theorem. It says for 2 by 2 matrices, if A diagonalizable, say with eigenvalues λ1, λ2, and eigenvectors. These could be the same. That's okay. V1 and V2, then 2 linearly independent solutions are e to the λ1t V1 and e to the λ2t V2 vectors. Okay, so we want to search for λ1 and λ2. In this case, they're going to be complex. And so we should do the same thing. We're going to get complex numbers everywhere. And then often it's nice to be able to write that as real valued independent solutions. So we'll practice doing that as well. So let's find the eigenvalues. Neat. Okay, we get -4 minus 2 plus 2. Okay, which equals lambda squared plus 4. So lambda equals plus or minus 2i. Okay, so we found, so notice that the eigenvalues come in complex conjugate pairs. So we found 2 distinct eigenvalues. So this matrix is diagonalizable. And now let's find eigenvectors. Lambda is 2i. We just need to do one of them because the other one will be the complex conjugate of it. So we look at 2 minus 2i. We want to find elements of the null space. Well, maybe I won't call this V1 or V2. Or not X1 either. W1. Okay, so we can row reduce this to get solutions, or there's this thing we can just, we know there's going to be a solution if we found their eigenvalues correctly, so meaning that these 2 rows are the same. They're just scalar multiples of each other. So we can just like make one of these, 1, and then the other one, whatever it has to be to get 0, for example. So I'll do something like, make the first one 1, and then this one has to be, negative 2 minus 2i over -4. Right, so that way when you multiply by the first row, you get 0, actually over 4, sorry. That way when you just multiply by the matrix, you should get 0. Right, if we multiply by the first row, we get 0, we'll get 0 in the first entry, and then maybe we can just check real quick that like this actually is a solution. So we just check. Let's see. 2. I'm just taking 2 times 1 plus negative 2 minus 2i times this thing. And then so what is, let's see, so when we just multiply this out, we get negative 4 plus 4i minus 4i plus 4i squared over 4. So we get negative 8 over 4, or sorry, yeah, negative 8 over 4, which is negative 2, and so you get 0. Okay, great. So we do get 0. Okay, so we found that this is an eigenvalue, or an eigenvector. So let's just sum that up. We get A is 2, negative 4, 2, negative 2. Eigenvalues plus or minus 2i. Eigenvectors are 1, and then what was it? 2 minus 2i over 4. And then the other one will be for the complex conjugate. So yep. In fact, we don't need fractions here. You know, why don't we just multiply by 4 everywhere? Make it a little cleaner. There. So those are eigenvectors for their corresponding eigenvalues. Okay, so that means that solutions are e to the 2it times this vector, and e to the negative 2it times this vector. Okay, so you know, one could say that this is the answer, that these are two solutions, but oftentimes it's nice to write these as real valued solutions because you know, usually we're solving differential equations for like a real physical system. You know, the easiest one being like a spring on or a mass on a spring, in which case these solutions are supposed to give you like displacements from 0 or from equilibrium. And so it's nicer to get like a real valued solution because like, what does it mean to be, you know, a unit I away from equilibrium? You know, that complex solutions don't quite make sense physically. And so we want to write these, right, two linearly independent real solutions would be nice. And we do that by just taking appropriate linear combinations of these to get real solutions. I'm slightly, so there's a question, there's confusion on how to visualize, interpret the vectors in the solution. I mean, that's kind of the point, that it's hard to visualize complex vectors, right? So this is just a vector of functions. I mean, it's hard, I mean, just to visualize, for example, this vector is already hard to visualize, right? Like, just even without the e to the 2it. I mean, the reason it's hard to visualize is because like this is living inside the vector space C2, which is hard to visualize because C, the complex numbers, is already you know, I'll say a two-dimensional real vector space. What that means is it already has two components to it, the real and imaginary part. And so taking vectors whose elements are in C means that this thing really has 4 components, kind of. So like, if you want to visualize it, you kind of need to be able to visualize 4-dimensional space, which is impossible. So it's already hard to just graph this vector, right? Because to graph complex numbers, you usually do like a real part and imaginary part. This would be to graph C, but how do you do C2? It's, you know, you can't really visualize it. You just, the best way you can do it is just pretend like each axis here is a complex axis. So like, and then just try to graph it, you know, and visualize it somehow. But it really is impossible, right? Like it's, you know, you're trying to graph something in 4D. But fortunately, you know, when we take like remember when we start with a linear system, something like this, like a single second order linear or differential equation, then we can convert it to two first order linear equations. And then when we get these solutions, all we do is take the first component, because that's the one we care about. And so then that reduces these vectors in C2 to just a vector, or just a complex number. And so that's easier to visualize. Okay, so how do we write down? Let's go back to writing two linearly independent real solutions. You got different eigenvectors. Okay, let's check. You got 1 plus I and 1. And I got 4 and 2 minus 2i. What if we multiply the first one by 2 minus 2i? What do we get? We get 2 minus 2i, and then what do we get on the top one? 1 plus I times this equals 2 minus 2i plus 2i minus 2i squared, so plus 2. So we get 4, which is exactly this vector. So these are actually, even though they look like different eigenvectors, they're actually scalar multiples of each other. Yeah, it's a little confusing with complex numbers. It's hard to see whether they're scalar multiples. With the real vectors, it's very easy to see when things are scalar multiples. Like if I take something and I look at, you know, like it's very easy to see like, oh yeah, these are scalar multiples. But with complex numbers, like it's, you know, a little harder. So in fact, why don't we just use your eigenvectors so we can keep consistent. So these are not wrong, but I'm going to replace these with your eigenvectors. So I can match your answer. Then why are they linearly independent? Well, these are not, right? 1 plus I and 4 comma 2 minus 2i are not linearly independent. But this and its complex conjugate are linearly independent. Right, so these two are linearly independent, and these two are, but not these scalar multiples. Yeah, so maybe you can check that. Check that. These two are not scalar multiples of each other. Sorry, not scalar multiples of each other. This is also a 1 here. Okay, so right, back to finding two linearly independent real solutions. So yeah, so the way we do this is we take appropriate linear combinations of our two solutions, and to get the real parts of it, right? And what we're going to do is we're basically just going to take the real part of this and the imaginary part, and those are our two real solutions. So I'll write that down. Two linearly independent real solutions are the real part of e to the 2it 1 plus I 1, right? I'm replacing, sorry, these. The errors are confusing. Not because they're wrong, just because we just want to replace them with these other ones. And the imaginary part, so these, if you take the real part of this vector and the imaginary part of this vector, sorry, this is a plus, and the imaginary part of this vector, then those are going to be two linearly independent real solutions. So, okay. And that's what we need to do. We need to figure out the real part and the imaginary part. So I'm going to go to a new page. I want the real part of e to the 2it 1 plus I1, and the imaginary part of e to the 2it 1 plus I1. Okay, so we need to break up each one into its real and imaginary parts. Is essentially what we're going to do. So we're going to use this formula, which is e to the 2it equals what? Right. E to the I times something is cosine of that thing plus I sine of that thing. So in this case, we have 2t. Right, so what's happening here is this 2t goes right here and here. And it's an e to the I theta equals cosine theta plus I sine theta. This is sometimes called Euler's formula. Well, really it's when t is specialized to something, but we'll just call it Euler's formula. Okay, so to do that, so then we can just expand e to the 2it in terms of cosines and sines. So this equals cosine 2t plus I sine 2t. We're multiplying it by 1 plus I 1. And so we can just break this up into imaginary and real parts. So, right, we can multiply the first one by 1 plus I. I'm going to cosine 2t plus I sine 2t plus I cosine 2t minus sine 2t. And then here we get cosine 2t plus I sine 2t. And now we have, let's break it up into real and imaginary parts. So the real part on the top one is cosine of 2t minus sine of 2t. And the bottom is cosine 2t. And here we have sine of 2t plus cosine of 2t. And so here are the real and imaginary parts. Are there questions on that? This is what you got, but the back of the book is different. Okay, let's look at that. It's like probably because they simplified in some way. What did they get in the back of the book? They might have gotten different. They might have started with different eigenvectors too. Because like remember, if you use these eigenvectors, 4 comma 2 minus 2i, then you're going to get something a little different. Because like these are two linearly independent solutions, but so is any linear combination of them, right? If I take a linear combination of them and replace one of them with the other, then you can get you know, different vectors, but like it'll be two linearly independent solutions. It's kind of like when I ask you for a basis, you could give me, I mean, there's infinitely many answers to find the basis. And so their solutions might just be different linearly independent solutions, but still valid nonetheless. So maybe you could tell me what they got in the back we can compare. Or you can just, you know, trust you did it correctly. Let's see, or I can look real quick for solutions. Is this, let's see. This is 9.6, number 1. They got 2 cosine 2t over cosine plus sine. And 2 sine t over sine minus cosine. Sorry, it's kind of bad handwriting. I was writing fast there. So sine minus cosine. Okay, so yeah, if I add these two vectors, if I add the first vector and the second one, the sines on the top cancel and I get 2 cosine 2t, and then I get cosine plus sine. So that gives me the first one by adding these two. And then if I subtract the two, I would get negative of this one. So this would be subtracting and adding. Let's call this 1 and 2. Adding 1 plus 2. Subtracting this would be a 2 minus 1. And so they're just both of these are just linear combinations of R's, and R's are linear combinations of theirs. So these are in fact both equally valid solutions. They're both 2 linearly independent solutions. You know, both are valid. Right. It's kind of like, you know, if I were to say, give me a basis of R2, and you gave me, you know, 1, 0 and 0, 1, and someone else gave me 1, 1 and 1, negative 1. You know, both of these are bases, both valid. You know, so it's just depending on what you give as an answer. Okay, so, but yeah, that's the general process for finding linearly independent real solutions to systems of differential equations with complex eigenvalues. Should we do another example of something else? I'll start from the beginning. Yeah, you'll notice that with real or with complex eigenvalues and complex eigenvectors, it's hard to say, to just compare easily to see if you're correct or not, because there's so many like valid solutions that you could get. For example, like there's so many different eigenvectors we could have written down. I mean, this is true for real eigenvectors as well. You can take any scalar multiple. But usually you can just tell pretty quickly if something's a scalar multiple of something else with real numbers, but with complex numbers, it's a little harder. And so likewise, it's a little harder to look at these two solutions and see that they're the same. Maybe we can do another practice one. So you can try doing this one. Or we can do something else. It's up to people. I don't have much of an agenda for today because we kind of have reached maybe the end of differential equations. For number 17, 9.5, can you explain the trajectory of solutions? Okay. 9.5. Look at this. Sorry, I'm just scrolling up to find it. Number 17. So we have a system, 1, square root of 3, square root of 3, negative 1. You find the eigenvalues, and then you find the eigenvectors. And you have to sketch the trajectory of the solution having an initial vector. Okay, well, that means we're going to have to solve it. So why don't I kind of do that? Why don't we just do two separate things going on here? Did you get the solution? So this is number 17, 9.5, number 17, a equals 1 square root of 3, square root of 3, negative 1. Well, it tells you eigenvalues. And it tells you eigenvectors. And what was the other one? 1, negative root 3. Right. Okay. And you want initial condition x of 0 equals negative root 3, 1. Yep. And okay, so the solutions, remember, because we have these, are e to the 2t root 3, 1, and e to the negative 2t, 1, negative root 3. So negative root 3. Okay, and so general solution is C1 times this. I don't know why I wrote it over here. Okay. So if you're given an initial condition, you can solve for some of the coefficients. Okay, actually, they're asking you to sketch the trajectory, so they don't give you a full initial conditions. They don't give you the derivative at 0. But you can solve for that, I guess, with this equation, ax equals x prime. So you can solve for x prime of 0 equals ax of 0. So you should get negative 2 root 3, 1. And so now you have two initial conditions. And so you can solve for C1 and C2 to get the actual solution. And then you can kind of just sketch that, I guess. I guess that's how I would think about this problem, or try to do this problem. Other than that, I would just kind of like start trying to draw some things. At 0, you have negative root 3 over 1. Or sorry, negative, something like this. And then its derivative is just, it's kind of going, derivative is negative. I don't know. It's kind of hard to like sketch really. So that way is a derivative. Yeah, I don't know. I don't know what they want as a sketch. Right. This is its value at 0, and then its derivative at 0 is in the same direction. So, and in fact, actually, like this is an eigenvector, so like, you know, it's going to move a little in this direction, and then it's just going to keep moving in this direction. So I guess what they're really asking you is just its trajectory along this path is just going to be straight out along the path. It's not going to move anywhere else. That's probably what they're going for. That like you have this, that whatever this function looks like, along this ray, it just like, it just doesn't deviate. It stays exactly along this ray. And same with 1 negative root 3. So along this ray, it's going to stay, oh gosh, I guess. Yeah. So you can, I mean, it's kind of interesting. Like along this blue ray, like you start at negative root 3, negative 1, and then you just continue, and then the derivative is still in that same direction, so it kind of just pushes you out as far as possible. Like you start here, and then as time goes across, or as time increases, you kind of just go to infinity. Whereas with this purple line, you might start here, maybe at t equals 0, let's say, if you were to start here, and then that's 1 comma negative root 3, and then its derivative at that time, if you multiply it by this matrix, would give you negative 2 times that. So that would be in the other direction. That would be in this direction. And so it's going to like bring it back to the origin. And then when it goes past the origin, its derivative is now negative that. So it's going to, as t increases, it's going to like oscillate back and forth. Right? That's what it seems like. Whereas this blue line, you know, I don't know. It's kind of a heuristic. Probably not that important. What is the answer to the question on the left? Yeah, let's do this one. What did you get for the eigenvalues and the eigenvectors? Plus or minus I, okay? Yeah, okay. And then what did you get for the eigenvectors? Minus 2 plus I, comma 1, and then it's complex conjugate. Yep. This one is for plus I. I assume this one is for minus I. Okay. And then the solutions are e to the it times negative 2 plus I, comma 1. We want to find the real part of this and the imaginary part. So this equals cosine of t plus I sine of t times -2 plus I coupled 1, which equals, we want to write it as it's real plus it's imaginary. And then those are going to give us general solutions. Okay, so the real part will be -2 cosine of t minus sine of t. And this will be cosine of t. And its imaginary part will be -2 sine of t plus cosine of t. And this will be sine of t. And so its solutions are exactly just these. -2 cosine of t minus sine of t. And if you want, you can scale these if you want, or some way clean them up if you want. But these will be two solutions. You could add like 2 copies of this one to that one if you want, or something. But yeah, these are your solutions. So. Let's do cosine. Okay. Well, I think like that's kind of most of the differential equations that we've talked about. We've talked about second order differential equations, how to solve them. We've talked about, I'll just write that, like maybe a recap on differential equations. So just like all the various topics. So we talked about how to solve second order homogeneous ODEs. And so to solve that, there's 3 cases. You look at, so that's AY double prime plus BY prime plus CY equals 0. And so then you look at AR squared plus BR plus C equals 0. And there's 3 paradigms. You have the roots are different, the roots are the same, and the roots are complex conjugates. And then you get various solutions. Okay, we've talked about second order non-homogeneous ODEs. Right, so you solve homogeneous, then you guess particular solution, particular, and plug in to get coefficients. This is sometimes called the Ansatz method, or the method of undetermined coefficients. Yeah. Right, because you have coefficients in your guess and they're undetermined, and then you plug it in to determine them. And then, okay, we've talked about systems of ODEs. This is AY double prime plus BY prime plus CY equals F. Systems of ODEs, you find eigenvalues and eigenvectors of A. And then, depending on whether it's diagonalizable or not, this gives you a solution. And if the eigenvectors or eigenvalues are real, you get different solutions. What else have we talked about? We didn't really talk about systems of non-homogeneous ODEs, so we probably won't stress that. And then we also talked about how to go from how to translate, I guess. How to go from the first one to the third one, how to translate. A single second order to a system of first orders. And that's kind of the recap on ODEs. The book covers more methods and more cases, but I think that's mostly what we covered in this class. So yeah, is there any questions? I think that's kind of most of what I wanted to talk about today. That's kind of ending differential equations. Yeah. I'll leave this up. And yeah, I think I'll just kind of be on here for other questions people have. A reminder that I have office hours today. And we can kind of just end early. I guess for ODs, all right, so I'll leave this page up for a little bit. And then we'll do another example about how to, we can just go over, we'll review next page. We'll review how to translate from the first to the third. Just to recap. Okay, let's consider this is just more practice. Consider the differential equation. Let's make it actually a little harder. Give me a sec. Let's consider this ODE. Okay, so we have a single ODE. It's a third order ODE, and it's got some coefficients that aren't scalars, and it's kind of non-homogeneous part, right? And we want to write this in normal form, by which I mean as AX equals X prime. So we're going to write this single third order equation into 3 different first order equations as a system of ODEs. So it's going to be a 3 by 3 matrix. Here's X. Here's X prime. Actually, I'm going to call these 0, 1, and 2 instead. Oh, wait, I guess because there's a non-homogeneous part, actually, we're going to have this extra F floating around. Which I haven't really talked about, but we can adapt this, not too much extra work. Okay, so let's recall how to do this. Remember that these X variables are supposed to represent the various derivatives of Y. So this first one is going to be our function Y itself. This second one is going to be Y prime. And this third one is going to be Y double prime. And we only want to go up to the n minus 1 because this x2 prime is going to be the third derivative. Okay, so that's what x2 is supposed to represent. We're going to make it equal to y double prime. Okay, and now we have to think about how to relate these two. So if we look at the first row, we multiply it by this first column. That means, what this term here times y of t plus this term times y prime of t plus this term times y double prime of t has to equal x0 prime. So x0 prime, what is this? If x0 is y of t, then x0 prime is equal to y prime of t, which we said is equal to x1, right? And if x1 is y prime, then x1 prime is y double prime, which we said is equal to x2. And then this is y triple prime of t, which we haven't set to anything yet. And so we're saying what linear combination of x0, x1, and x2 gives us x1, right? We want a linear combination of x0, x1, and x2 to give us x1. We should just have 0, 1, 0. Okay. And then the second column, we want a linear combination of x0, x1, and x2 to give us x2 of t. So that should be 0, 0, 1. 0, x0, 0, x1, and 1, x2 gives us x2. Okay, and now the third column, we want a linear combination of x0, x1, and x2 to give us y triple prime. And here's where we're going to use this ODE, right? So we want a linear combination of y, y prime, and y double prime to give us y triple prime. I'll do this in red. Right, so we can solve for y triple prime as a linear combination of these ones. We get that it equals, there's a 10y in here. So I'm just rewriting this, I guess. Y triple prime. I'm going to write this as y triple prime's over here. So rewriting star, we get it equals 10y minus 2ty prime. And then we have an e of t. And there's no second derivative. Yeah. And so this gives us our coefficients. So we have 10, y triple prime equals 10 times y, that's 10 times x0, negative 2t, x1, and there's 0 copies of the second derivative. And then we have this extra e to the t. So we have, because bringing it over is a minus e to the t. So I'll do this. I just rewriting the differential equation. Okay, and now that's our normal form. Here's our matrix. Here's x, x prime, and here's f. So just some practice on converting a single ODE to normal form. In general, you're just going to get A is going to be mostly zeros and ones. It's going to be 1 all the way to the end. It's going to be 0 on the diagonal, and then this bottom row is going to be where you use the differential equation. Okay. Would we be expected to solve equations with non-constant coefficients? No. No, we haven't gone over that, so you're not expected to know how to solve this. You should not know how to solve this, in fact. If you know how to solve this, great. I think that might be, well, not know. I don't know if we've gone over techniques in the book for how to solve this, or if it even has a solution. Yeah, it has a solution. I know how to solve it. Okay, well, kind of stay on for a little longer if anyone has questions. Otherwise, you're welcome to do whatever. Again, I have office hours today at 3:30.